Hello students. Today we shall start with the new section of the chapter coordination compounds. So basically today we will basically discuss on the bonding in coordination compounds, and there are several theories that are helpful tools to explain the bonding in coordination compounds. So we shall start with the valence bond theory first. In our last sessions, we have basically discussed and mainly focused our discussion on the Werner's theory of coordination compound. So I had told you about that. That's the Werner's theory was actually the first theory to describe the bonding in the coordination compounds. So Werner was the first one who first described this theory and put up some postulates to explain the different kinds of bonding in the coordination compounds. But there were some drawbacks that were found in the theory, and this theory could not answer these three questions mainly. So the questions were arising regarding the bonding in coordination compounds, and Werner's theory was successful in answering most of them, but there were some questions which were unanswered by the Werner's theory. So these are the questions. First one is the why do only certain elements possess the remarkable property of forming the coordination compounds, not all. So in the periodic table, we have these S block elements, we have these P block elements, we have this D, and we have these F block elements. Out of these, most of the D block elements and some P block elements are the ones who are able to form the coordination compounds only, not all the elements. We have these S block elements such as sodium, lithium, beryllium, magnesium, and we also have such very common F block elements. Among those, I have told you about the lanthanides or the inert transition elements, or the F block elements, the actinides. So they do not form such kind of coordination compounds. But all the D block elements are actually most famous to produce the coordination compounds. There are some P block elements that can actually produce coordination compounds, but the number is not that much. So basically the transition element or the D block elements are the only elements which possess this remarkable property to form coordination complexes. So Werner's theory is unsuccessful in answering this question. Why do these certain elements possess this distinct property? Second one is the why the bonds in coordination compounds have directional properties. So in the coordination compound, in the last class, I have told you about these equatorial bonds and the axial bonds. These are the things I have told. So basically, if we can draw an octahedral complex, suppose this is an octahedral plane, and we have the metal center in the middle, we have this ligand here, we have a ligand in the four vertices of the square, and we also have these axial points where we have two ligands. So basically you can see in this plane where four L ligands are present are actually termed as the equatorial plane, or these are the ligands, they are termed as the equatorial ligands. And also we have this axial position, we have two ligands and they are termed as the axial ligands. Also we can think of the basic compound here about the PF5 molecule. So PF5 is a trigonal bipyramid. PF5 is the molecule which is actually structure is having a TBP structure. So in this case, the phosphorus atom is present in the center, and we have two fluorine atoms. One is above the fluorine phosphorus, another is the top of the phosphorus. So here you can see we have three fluorine atoms here. So we have this PF5 molecule here. Here we have these three F atoms in the equatorial plane, and we have these two axial fluorine atoms in the equatorial plane. So in this case, what happens? These three fluorine atoms, we can term those as the equatorial fluorine. And these two fluorine atoms we can term as the axial fluorine. So these three fluorine atoms are equatorial and these two fluorine atoms are axial. Now we shall have to have the same analogy in this Ml6 octahedral complex also. Here you can see these green dotted L's are in the equatorial plane. That's why these four L's are actually equatorial. And if you can mark the other two L's on the red dots, this L and this L, these are actually two L axials. So this is the directional property of the ligands in the coordination compound having a general formula Ml6. So that is not actually explained well by the Warner's theory of coordination compounds. Lastly, we have why do coordination compounds have characteristic magnetic and optical properties? Now, in the last class, I have told you about the optical properties present in the coordination compounds. They can be cis isomers are optically active. They can be trans isomers are optically inactive. So these things are not actually explained by Warner's theory, WT. So Warner's theory is basically denoted by WT of coordination compounds. So Warner's theory is unable to explain why these coordination compounds have different optical properties. Also, they have characteristic magnetic properties also. So in the last class, I have told you about this mu value, which is spin only value, which shows the magnetic moment of the complex, which is designated as root over of n into n plus 2. In the unit is Bohr magneton. And this value actually arises in several coordination compounds depending upon their magnetic properties. So Warner's theory is also unable to explain how and why does these characteristic magnetic and optical properties arise in coordination compounds. So when Warner's theory was unable to explain how these things are arising in coordination compounds, these characteristic diagonal or directional properties, also these magnetic and optical properties, and also this why the specific elements are there to produce the coordination compounds. Not all elements in the periodic table is able to form a coordination compound. So that's why several theories have been proposed to explain the bonding in coordination compounds. First one is the valence bond theory, which is one of the most popular theories. So many approaches have been put forth to explain the nature of bonding in the coordination compounds. So these are the list. You can have a look at that. First one is the valence bond theory, abbreviated as VBT. Second one is the crystal field theory, abbreviated as CFT. Third one is the ligand field theory, abbreviated as LFT. And the last one is the molecular orbital theory, which is termed as MOT. So among all these theories, the first two theories we will discuss in our present scenario. So basically, for you guys to understand the details of ligand field theory or the molecular orbital theory, these are on a matured or the advanced stage theories. So in this position, in your position, you are actually able to understand the valence bond theory and the crystal field theory. That is, the first two theories are actually sufficient enough for you guys to have a look at that. So we shall start with the valence bond theory first. In our today's section, we will basically focus our talk on the valence bond theory, and we shall start a little bit with the crystal field theory. And in the next session, I will complete the chapter by totally explaining the crystal field theory in a nutshell. So we shall start with the valence bond theory. So valence bond theory is actually a very well-known concept that was actually discovered way earlier. So according to this theory, we have this metal atom or ion. You can see and have a look at the principle over here. The metal atom or ion is under the influence of ligand, and it can use its n-1d, ns, np, and nd orbitals for hybridization to yield or to produce a set of equivalent orbitals of definite geometry, such as octahedral, tetrahedral, square planar, and so on. Now, these hybridized orbitals are allowed to overlap with the ligand orbitals. So we have from the metal side, we have these hybridized orbitals, which we are terming as HO. And from the ligand side, we have these ligand orbitals, which are termed as LO. Now we have these metal orbitals, metal-based orbitals. We have these ligand-based orbitals. Metal-based orbitals are actually hybridized. You can see these are the orbitals that are actually involved in the metal-based hybridization. N-1D, NS, NP, ND. So basically, when we will talk about this 3D kind of transitional metals, we will talk about the 4S, we will talk about 4P, we will talk about 4D, and also N-1D. That's why it is termed as the 3D. So these will be the orbitals that we will discuss when we will talk about the 4S, 4P, 4D, and 3D. Now, these metal-based orbitals are hybridized. We have these ligand-based orbitals also. Now they can donate the electron pairs for bonding. So there will be a bonding between the hybridized orbital of metal and a ligand orbitals of ligand. Now these things are basically denoted here in the form of a table. So this table is very crucial for you guys to understand, or you guys have to memorize the things at first. So gradually we will have a grip on that, how these things are actually acting. First one is the coordination number. So we shall start with the coordination number. So about the coordination number, we have discussed earlier in our section of the coordination compounds. So the coordination number can vary from 4 to 6. You can see in the first row, the coordination number is 4. So for coordination number 4, there are, you can see the two options are there. First one is the type of hybridization, and the third column is distribution of the hybrid orbitals in space. This is nothing but geometry of the complex. So you might be astonished by seeing this large thing denoted or written over here, but nothing to worry about, because this thing actually denotes the geometry of the corresponding compound. So here you can see the distribution of hybrid orbitals in space. So in space, how the orbitals are actually located, that is actually determining the geometry of the complex. So here you can see when the coordination number is 4, there are two different types of geometries. First one is the tetrahedral and the second one is the square planar. So when it is tetrahedral, the type of hybridization is sp3. So no d orbital is involved in the tetrahedral kind of geometry. But when the distribution is square planar, the geometry around the metal center is square planar in nature, then the type of hybridization will be dsp2. So d orbital will be involved in the square planar geometry. So when the coordination number is 4, then we will have these two sets of hybridizations, sp3 and dsp2. You can have a look at that, how we will remember this thing. You see here you have to calculate the number of orbitals. So the number of orbitals must be equal to the coordination number. Suppose we have this sp3 tetrahedral. So we have one s orbital and 3 p orbitals is equal to 4. That 4 is actually this one. Also, if we can take up the example of dsp2, we have 1 d orbital, we have 1 s orbital, and also we have 2 p orbitals. Total is counting for 4. That 4 is. Similarly, you can also calculate the things over here. This is sp3d. We have 1 s, 3 p, and 1 d. Total is 5. And in case of 6 coordination number also, you can see the type of hybridization is sp3d2, 1s, 3p, and 2d. So 1 plus 3 plus 2 equals to 6. So this is the trick basically for you guys to remember how the coordination number and the type of hybridization, these two things are related to one another. So we have this coordination number 4. We have two different kind of hybridizations over here. First one is the sp3 and the second one is the dsp2. sp3 corresponds to the tetrahedral geometry and the dsp2 hybridization corresponds to the square planar geometry. Now, we have this coordination number 5 also. So basically, when I taught you about the PF5 molecule, it was actually having the geometry trigonal bipyramidal. So let me show you about the geometry in this case. So let me first erase the things to have some space over here. So this is the geometry of a tetrahedral moiety. The central atom is sitting right here in the middle of the tetrahedron. We have ligands at each of the vertices. So this geometry is basically the tetrahedral geometry. That is the tetrahedral. Now we have the square planar geometry. So square planar geometry, you can actually draw it quite evidently from the name. The central metal atom is actually lying in the midpoint of the vertices. This is the square planar geometry because this is a square and this is a plane. That is a square planar geometry. Now this is the trigonal bipyramid geometry, which is quite interesting to draw. In trigonal bipyramid, we have to first draw a triangle, and in the midpoint of the triangle, we have to write the metal atom. Now, from the top of the metal atom and to the bottom of the metal atom, there are 2 points. This is the trigonal bipyramidal. Because this is a triangle, this trigonal, and if you can join these vertices to this point, it will look like a pyramid. And there are 2 such points, one above the metal and one below the metal. That's why the bi things come here. That's why it is bipyramidal. So that's why this geometry is termed as the trigonal bipyramid geometry, which is basically TBP. This one is the square planar geometry, which is basically abbreviated as SQPL. And this one is termed as the tetrahedral, which is designated as TD. This D is actually suffix here. Now we have the most common octahedral geometry over here. So octahedral geometry is quite easy to draw. Just in the square planar geometry, you have to add 2 vertices, one above the metal and another below the metal. So that will account for your octahedral geometry. So this is octahedral. Now, basically, I have taught you about 5 different geometrical structure or geometries here. Different kind of distribution of orbitals are there in the space. First one, this is the tetrahedral. This is the square planar. These 2 things are actually having coordination number 4. Now we have this trigonal bipyramid geometry. There is also another geometry. It's preliminary stage. So for this, you have this coordination number 5. And in the last case, you have this octahedral geometry, which is having the coordination number 6. So basically, at this point, what we know, we know about the type of hybridization, we know about their coordination number and the geometries of the metal complexes. Now here you can see in case of the coordination number 5, the hybridization is sp3d, which accounts for the trigonal bipyramidal geometry. And we have these two kind of hybridization with the same coordination number, that is 6. Now you will be surprised that how these things are written over here. You can see one is starting from S counting to D, and basically these two things are same. It is sp3d2 or it is d2sp3. Just this d2 comes prior to the S, and it has become this d2sp3. But I have written these two hybridization separately. Why it is so? Because I will talk about these things quite elaborately in our later slides. So basically the first one is the outer orbital complex, and the second one is the inner orbital complex. Now what is defined by these two terms we will discuss in the later slides. So at this point of period, we are actually known of the fact there are 3 different types of coordination number generally in the valence bond theory: 4, 5 and 6. For 4 coordination number, we have 2 different kind of geometries: tetrahedral and square planar. Tetrahedral corresponds to sp3, square planar corresponds to dsp2. Then we are coming to the coordination number 5, which is having the hybridization sp3d, which is having the geometry trigonal bipyramidal. And in the last case, when we are having the coordination number 6, the type of hybridizations are 2 here too. First one is the sp3d2, the second one is the d2sp3, and both of them corresponds to the same geometry, that is octahedral. Now for your information, I would like to tell you that the octahedral geometry is most common in case of the valence bond theory. So how this valence bond theory is proving to be helpful to predict the hybridization or the geometry of a specific complex. So with the help of 3 different kind of examples, I would like to elaborate these things to you. Here also I will clarify how this sp3d2 and d2sp3 things actually differ from one another. What is meant by the inner orbital complex, or what is meant by the outer orbital complex, that we will also discuss in this slide. So basically we will start with the complex cobalt NH3 whole 6 3 plus. Now we have this cobalt 3 plus. Now you know that this cobalt 3 ion is here. Let me draw it here. So cobalt 3 is having the electronic configuration of D6. So the D6 is the electronic configuration of the cobalt. So to be precise, this is actually 3D. So it is 3D6. Now, if we can write about the electronic configuration of 6D electrons in a 5D orbitals, we will have this kind of scenario. So we have 5D orbitals over here, and we have total 6 electrons. Since ammonia is a neutral ligand and the net charge of the species is 3 plus, that's why the oxidation state of cobalt here is +3. And cobalt is having the configuration 4s2 3d7. So 9 electrons are there. Since it is +3, so 3 electrons will be omitted. So we will have this 3d6 configuration. Now let us actually fulfill the orbitals with the help of electrons. So 5 actually put here, and the last one is actually here paired up. So this is the 3d6 configuration of cobalt +3 ion. And also if you have read about the orbital filling, then we have this 4s orbital here, which is vacant after 3d, and also 3 4p orbitals here. So these are 4p and this is the 4s. All these are vacant in nature. because no electron is there to fulfill. Now, since now ammonia is the ligand over here. Now, basically, when we will talk about the nephloxetic series or the field strength of the ligands in the later classes, I will be discussing about the nature of the ligand. For this present scenario, you have to remember the fact which are the strong field ligand and which are the weak field ligand. So ligand field theory here actually comes into picture, but we will not discuss anything about the ligand field theory, but we will know which kind of ligands are actually strong field and which kind of ligands are weak field. So for your information, I will tell you this ammonia, this is the ligand over here, is a moderately strong field ligand. Ammonia. And since the cobalt is in a high oxidation state, that's why their pairing causes. So when the ligand field strength is quite high and we have a metal which is a high oxidation state, that is over class 2 oxidation state, within the electrons will get paired up. So there occurs the pairing of the electrons. So what will happen here? We are having this 3d6 kind of electronic configuration and we have these 4 unpaired electrons. Now in presence of the ammonia ligands, which is a moderately strong field ligands, these 4 electrons will be paired up. So we will have this 3d6 as a 3 pairs. So these 2 electrons will get paired up with these 2 electrons and will produce 2 vacant positions in the 3d orbital of the cobalt 3 plus. And still we have these options left. This one is 3d, this one is 4s, and these ones are 4p. Now we are having these ammonia molecules over here, and 6 ammonia molecules are there. Because you can see there is either it will be an octahedral geometry complex, because I have told you like octahedral geometry complexes are well known in the coordination compound world. So here these red electrons are actually those donated by the ammonia molecule. So ammonia will donate 6 pairs of electrons. Here you can see 6 ammonia molecules are there and each of ammonia possesses 1 pair of electron. So each ammonia will donate 6 electron pairs to the vacant orbitals of this cobalt 3 plus complex. So here you can see we have 6 orbitals, 2 plus 1 plus 3, and we are having 6 electron pairs getting accepted from the ammonia molecule. So all the orbitals are fulfilled. Now we can see that no other electron is actually unpaired here. So the compound is actually showing no paramagnetism because no unpaired electron is there. That's why it is a diamagnetic compound. Or you can see, or you can say the spin parity has been dropped in this complex because the spin have been paired. You can see the 4 electrons were there, but they were paired up. And since they are paired up, it is termed as the spin paired complex. And since the spin has been paired, that's why the magnetism has been dropped. It has become a diamagnetic compound. That's why it has become a low spin compound. It's a low spin complex because the spin is actually low. The total diamagnetic properties is there. No paramagnetism is found in the compound. And because the inner 3d orbital is used here in the bonding, you can see the 3d orbitals were there, but this inner 3d orbital. So why it is inner? Because you can see we are having this 4s orbital over here and this 4p. This complex does not actually use the outer 4d orbital. No, it rather uses the inner 3d orbital because 3d is coming lower in energy than 4s. So the inner orbital is actually used here for bonding. That's why it is termed as the inner orbital complex. So that's how we can predict the hybridization and the geometry of a specific compound or coordination complex in a with the help of the VBT. So what happens in this case? I will also again repeat the thing in a nutshell. We are having a 3d6 metal ion which is having 4 electrons in unpaired condition. It is having a 4s vacant and 4p vacant orbitals. Now, in presence of a moderately strong field ligand, which is ammonia, so all these 6 electrons will get paired up in the cobalt 3 plus center. So then we will have this kind of geometry or the electronic configuration where the 6 electrons are paired in 3 different sets in the 3d orbitals. Now 2 3 orbitals will now become vacant. One is coming from the 4s and 3 are coming from the 4p, and all the 6 hybrid orbitals will then get donated electrons from the ammonia molecule. Ammonia has 1 pair of electrons for donation. So this ammonia will donate electrons in the vacant 3d, 4s and 4p orbitals over here. And that's how, since the inner 3d orbitals are utilized here for bonding, that's why these are termed as the inner orbital complex. Since the spin has also dropped, that's why it is a spin pair, or you can say the low spin complex. And since the coordination number over here is 6, that's why it is termed as the octahedral complex. So these are the basic parameters that are discussed in the first example to predict the hybridization of a specific complex, which is here cobalt NH3 whole 6 3 plus. Now we will move down a different kind of complex, which is cobalt F6 3 minus. So we shall talk about this different complex, which is cobalt F6 3 minus. Now the main thing is it is also containing this cobalt 3 plus ion, because you know F minus is an anionic ligand, and we have 6 F minus are there, and the net charge of the complex is -3. So if the cobalt oxidation state is X, so X minus 6 will be -3. And by solving the equation, we will get the X will be +3. So the oxidation state of cobalt is also +3 here. So the scenario remains the same when no ligands are there, which is 3d6. Now the fluoride ion, unlike ammonia, is a weak field ligand. So weak field ligands are unable to pair up the electrons in the metal center. So what happens in this case, the 4 electrons that are unpaired here remain unpaired. They do not get paired like in the previous case. So when the fluoride atoms will come into picture, we will have this scenario. We have 1 4s here, we have 3 4p here, and also in the higher energy, we have 4d here too. Now here in this case, you can see 3d6 is already filled up because the electrons are not paired up, because F minus is not a strong field ligand. It is a weak field ligand. So what happens in this case, the F6, F minus are here. All are negatively charged. So we have this 3d6 over here, and we have this 4s, we have the 3 4p, and we have this outer d orbitals, which is 4d. Since these inner d orbitals cannot accept electrons from the F minus, so basically cobalt 3 plus has to use the outer 4d orbitals to accept the electrons from F minus. So here all the electrons, 2 electrons will be paired up from F minus, and 6 orbitals will be fulfilled. So what is the scenario over here? So in this case, the scenario is such that the 4 electrons are actually unpaired here. So we have 4 unpaired electrons, and the outer 4d orbitals are involved in the bonding. So that's why it is termed as the outer orbital complex, because not the inner 3d orbital, but the outer 4d orbitals are used in bonding. And since the electrons are not actually paired up here, that's why it is termed as the spin unpaired complex. And also since the number of unpaired electron is 4 here, that's why it is termed as the high spin complex, because the spin is quite high. So the mu will be root over of 4 into 4 plus 2. So root over of 24 Bohr magneton. So around 5 Bohr magneton will be the spin only magnetic moment of the cobalt F6 3- complex. So these are the basic difference between between two different complexes which are having same metal atom in the center, but the ligands are actually different. So these two examples were from the octahedral geometry. But not only octahedral geometry we have to talk about, but there are different geometries also while talking about these cases. Now, let's talk about some different geometry complex, which is NiCl4 2-. So this is the complex NiCl4 2-. Now, likewise, fluoride is also a weak field ligand. So all the halides are actually weak field ligands. Now, we have this compound of nickel, which is having a nickel plus 2 center. Now, nickel plus 2 is D8. So if you can draw this over here, we will draw first 1, 2, and 3, 4, 5, and then we will start pairing up the electrons according to Hund's rule. 7, and this is 8. So basically, in case of nickel plus 2, we are having 2 unpaired electrons in the 3D orbital. So 2 unpaired electrons are there in the nickel plus 2 system, and then we are having this 4s and 4p orbitals over here. Now we have 4 Cl- ligands. So 4 Cl- ligand, each of them will donate 2 electrons in the 4s and 4p. So this is 4s and this one is 4p. So 4 Cl- ligands will donate their 2 electrons each to the 1s and 3 4p orbitals, and these 2 3D electrons will remain unpaired. That's why this is becoming a high spin complex, tetrahedral high spin complex. So this is nickel 2. So that's how we can actually predict the hybridization of a complex using the valence bond theory. So when we have talked about the bonding in the in this coordination compound, we are actually able to explain the different kind of hybridizations in the and different kind of geometry, different kinds of coordination number. So basically, in this case, we will talk about the magnetic properties of the coordination compounds. So this magnetism is actually quite relevant while talking about the coordination compound. They can be measured by the magnetic susceptibility experiment. Now the results can be used to obtain information about the number of unpaired electrons, and hence we can draw about the structure of the compound. So with the help of the magnetic property, we can actually predict the structure, or you can say the geometry of the coordination compounds. Now, basically, I have listed some values or species over here, and also the configuration that is will be helpful for you guys to understand. So firstly, we'll start with the species. So species is titanium 3. We have the electronic configuration of titanium 3 as D1. You all know, we have all known about the electronic configuration, how to draw them, how to correct them, or how to denote them. So basically, we are having the electrons over here. Number of unpaired electron is 1 because we have only 1 electron left. So it will be 1. Now we are having this vanadium 3 system, which is having the electronic configuration D2. So the number of unpaired electrons will be 2. So it is quite simple because we shall one by one fill up the electrons. Again, we are having the chromium 3, which is D3. So it is the number of unpaired electrons is 3. So basically, when we will calculate the magnetic moment, we will use this old equation, which is root over of n into n plus 2 in Bohr magneton. Bohr magneton is the unit, and this is the n. this column stands for the N, which is number of unpaired electron in the system. Then we are having chromium 3, which is having the electronic configuration D3, so the unpaired electron is 3. Now up to the coordinate, up to the electron number fulfillment of 3, the thing is quite simple and quite easy to understand. But whenever the more than 3 electrons are coming into picture, so when n is less than equal to 3, it is quite easy for understanding. But when n is actually greater than or equal to 4, then the thing starts becoming quite complicated over here. So that is the complications that I will address over here, and then I will suggest you guys some basic tricks to understand how these complications can be overcome. So we are having this electronic configuration D4. So whenever I have told you, whenever the number of electrons is going beyond 3, starting from 4, then 2 options already come into picture. First one is the high spin option, and the second one is the low spin option. It's the HS. HS is the high spin option. LS is the low spin. HS is the high spin. LS is the low spin. HS is the high spin. LS is the low spin. Now, in case of chromium 2 or manganese 3, the electronic configuration is D4. So basically, you would argue how these complications arise, because basically it will be just 4 electrons we have to fulfill in the d orbitals over here, and we are having 4 unpaired electrons. Quite simple. But why I am writing it is the 4 H's in the high spin and 2 in the low spin. So here actually we are actually drawing this because all the orbitals are degenerate. We are assuming this as degenerate orbitals. But actually, in case of the ligand field, the degeneracy can be lifted. So here the 5d orbitals are actually, degeneracy is lifted by 2 orbitals, which is the lower one is termed as T2g orbital, and the upper is a high spin or high energy orbital is termed as the Eg orbital. These are not to be taught in this scenario because all these things are part of the crystal field theory, which we will discuss briefly or quite elaborately in the next class. But to understand the magnetism of the coordination compound, the basic thing of crystal field theory has to be brought here. So here you can say the T2g orbitals are 3 different sets of degenerate orbitals, and Eg is the 2 different degenerate states of orbital. And these 5 orbitals, degeneracy is lifted here. Now you can actually fill up the electrons over here. When the T2g is 3, when the d orbital is having 3 electron, we will have no such difference than the degenerate orbital. Up to 3, it's okay. You can see 1, 2, 3. In case of this also 1, 2, 3. But whenever another electron is there, whenever we are talking about a D4 system, then we have to argue where this 4th electron will go. Whether it will go to Eg or it will be paired up in the T2g. So then if it is going to the Eg electron, Eg orbital, then we are having 4 unpaired electron. That is the high spin system. But if this electron is actually getting paired up over here, so if you can erase this one from here, rather this electron will be paired up here. So then you can see the 2 electrons are actually free here. That's why in the low spin system, the number of unpaired electron is 2. But in case of high spin system, the number of unpaired electron is 4. So this is the scenario in case of the crystal field theory, where we can basically say how the number of electrons are there depending upon the ligand system. So when the ligand is having a high field strength, then this spin pairing will occur. So we will have the low spin complex. But when the ligand is actually having weaker fields, then the spin pairing will not occur. So then the 4th electron will go to the Eg orbital. Then we are having these 4 high spin complex which are having the 4 unpaired electrons. Likewise, in case of the Mn2 or Fe3, both are the D5 system. So we are having this D5. So we have 1, 2, 3. So in high spin scenario, it will be D5. So we are having the 5 unpaired electrons. But if we can have to pair up the electrons in the low spin scenario, then we'll have to write 1, 2, 3. Then we'll start pairing up over here. It will be 4 and it will be 5. So we are left with 1 unpaired electron. Here we are left with 5 unpaired electrons. Here we are left with 1 unpaired electron. So in case of D5, two different scenarios are also present. Now we are having the D6 scenario. So D6 scenario, so also we are having two options over here. One is the high spin option, and other is the low spin option. So here what happens? First one is the high spin option. You will write 1, 2, 3. Then we are high spin, so we will fill up EG first, and then we will start pairing from that bottom. So here we are having 4 unpaired electrons. That's why the high spin is 4. So sorry for the mistake over here, because LS, it is not LS, it is actually HS, because it's a high spin scenario. But what happens the low spin scenario? 1, 2, 3, and then we will pair up the electrons here only 4, 5, and 6. So no unpaired electron is here because it is a LS system, low spin system, no unpaired electron. This is the case of the cobalt NH3+6 compound that I have taught you in the last slide. What happened in case of CO NH3+6, it was an inner orbital complex. All the electrons were paired up, and D2sp3 was the hybridization. But you can have a point. What happens in case of the higher electrons, higher electron counts also? Why I am talking about more about the 4, 5, 6. So n is greater than or equal to 4, it is okay. But whenever n is also greater than or equal to 7, again, we do not have any problem, because then also both the things will be equal. So it is quite surprising. Let me show you with the example. Let's say we are talking about the D7 system. So we are having this D7 system over here. So 1 electron D7. So one I will fill up in the high spin mode, and another I will fill up in the low spin mode. D7 system here. 4, 1, 2, 3, 4, 5. Then we are talking about the high spin. Then we will, for this system, we are having this. In case of this, we are having 1, 2, 3, 4, 5, 6, and 7. So we are having 3 unpaired electrons. So then we are having 1, 2, 3. Then we will pair up 5, 6, and then we are having 1 electron left. So in case of D7 also, in high spin case, we are having 3 electron. In low spin case, we are having 1 electron. So if we can extend the analogy to the D8 system, so one we will fill up in the high spin, and other we will fill up in the low spin. So first high spin, 1, 2, 3, 4, 5, then 6, 7, 8 in the high spin. But if we can fill up this in the low spin, 1, 2, 3, 4, 5, 6, then we are having 7, then we are having 8. You see, both these electronic configurations are just the same. Here also we have 2 unpaired electrons in the EG. Here also we are having 2 unpaired electrons in the EG. So from n is greater than or equal to 8, the thing is quite same. N is less than or equal to 3, the things are actually same. So whenever we are having n is equal to 1, 2, 3 and 8 to 10, then we do not need the help of the crystal field theory, because in those cases, both the high spin or the low spin scenarios are same. But whenever we are having the midways from 4 to 7, then the thing actually becomes quite complicated, because in those cases, the high spin or the low spin things are actually termed as the fully different. So what the vast things we have discussed over here, we will again discuss in the next class of when we will talk about the crystal field theory. So here are the quite examples. First one is the MnCN6 minus, which is Mn3 plus. Now cyanide is a very strong field ligand. So you can see it is Mn3 plus, so it is D4. So it is cyanide is a high, is a very strong field ligand. So it is having a low spin complex. So the number of unpaired electron is 2. Unlike MnCl6 minus, which is having Cl minus as the unpaired, Cl minus as the ligand, which is a weak field ligand. So it is having a high spin scenario, for the unpaired electron is having 4. When talking about the FeF6 minus and the FeCN6 minus, both are having Fe3 plus, but F minus is a weak field ligand, and that's why it is having only one unpaired electron, because it is having this. So FeCN6 minus is a low spin complex having one unpaired electron. Likewise, we are having this COF6 minus and CO oxalate 3 minus. Now oxalate is a strong field ligand and cobalt 3 plus is there. That's why all the compounds will, all the electrons will be paired up. So we are having this low spin zero magnetic moment complex. But in this case, COF6 minus, 4 unpaired electrons are there. So it is paramagnetic in nature. So depending upon the ligands that are bound to the metal center, the number of unpaired electrons are actually calculated. Now let's talk. We will by this slide we will draw the conclusion to our this section, the limitations of the valence bond theory. So every theory has some kind of limitations. Just like Warner's theory was able to demonstrate or illustrate many of the examples, but valence bond theory was not actually able to answer also several questions. Though it was a helpful tool in understanding the things, but it was actually unable to answer several questions. First one is it involves several kind of assumptions. So in the valence bond theory, many things are actually, so one of the major shortcomings is it actually involves many assumptions. So much assumptions are actually there in the valence bond theory. Second is is unable to explain the color. So regarding the color exhibited by the coordination compound, there was no such explanation. It does not even give the quantitative interpretation of the magnetic data. That's why the crystal field theory comes into picture. It does not also give any quantitative explanation of the thermodynamic or the kinetic stabilities of the coordination compounds. It's also not able to make any exact prediction regarding the tetrahedral or the square planar structure. So you don't know what ligands will produce the tetrahedral geometry, what will be produced by the the square planar geometry. So basically here also crystal field theory comes into picture, which tells these ligands are there, so it will produce a tetrahedral compound. These ligands are high strong field ligands, those are produced by the square planar compounds also. And lastly, it cannot distinguish between the weak and the strong field ligands, which is the major drawback or the shortcoming of the valence bond theory. So according to valence bond theory, ammonia, or we are having this bipyridine, or we have ligands such as cyanide, or we are having ligands as NO, or we have ligands such as OH minus, or we are having ligands such as F minus. So all the ligands are actually similar to the valence bond theory. They cannot distinguish between the ligand field strength. They cannot tell which one is a strong field ligand or which one is a weak field ligand. So because of all the shortcomings of the VBT, the crystal field theory or the CFT is actually coming into picture, that we will discuss in the next class. The basic 2 points are to be noted here. First one is in crystal field theory, an electrostatic model is considered, where the metal-metal bond is to be, ligand bond is to be ionic, which is arising purely from the electrostatic interaction from the metal and the ligand. So metal is actually having a delta positive charge and the ligands are having a delta negative charge. So there occurs a significant electrostatic interaction between the metal and the ligand. That is the assumption in case of the crystal field theory. And also ligands are treated as the point charges. In case of anions and in case of neutral molecules, they are termed as the point dipoles. So in case of the ligand, it's a ligand base, is the metal base, they are termed as the point dipoles or the point charges. So these are the basic two assumptions, and with this knowledge in our hand, we will step forward towards the next class, where we will discuss about the crystal field theory, the magnetism or the color shown by the coordination compounds. So for this class, this is it, and we shall talk about the crystal field theory in the next class. Thank you.